Introduction of mine ventilation. Outline. Overview. The design of large-scale subsurface ventilations and environmental management systems is a complicated procedure with numerous interconnected elements. To guarantee that the effects of such interactions are not neglected, system analysis principles should be employed. However, during the design exercises, ventilations and the subsurface environment should not be considered separately. They are the essential component of the mines or subsurface facilities' overall design. History of mine ventilation. European miners built tunnels into shock deposit into quiz of length between 4000 and 1200 BC. Early plant miners constructed brushwood fires and the working phases. The archaeologists discovered at Green Graves in south of England, apparently to soften the rock. Those Neolithic miners, on the other hand, could certainly have missed the air current caused by the fire. The use of fire to increase airflows was rediscovered by the Greeks, Romans, medieval Europeans, and British industrialists during the Industrial Revolution. This technique began in 1911 and continued until 1986 in the United Kingdom, when it was replaced by an electrical gas detector known as electrical nose. Today, deepest mines are approximately 4 kilometers below, necessitating a complex ventilation system to provide a safe and consistent airflow. Environmental control of the mine atmosphere. Purpose and importance. Ventilation is the most flexible atmospheric control instrument in the mining engineer's arsenal. It is the method used to achieve the majority of subsurface environmental management. Mine ventilation is simply the application of fluid dynamics concept to the movement of air in mine apertures. Ventilations, as the major means of quantity management, is in charge of the circulations of air, both in quantity and directions, throughout the mine. It is one of the constituent processes of total mine and conditioning. The simultaneous management of quality, quantity, and temperature, humidity of mine air within set limits. The importance of mine ventilations and air conditioning has not just newly been recognized. From onset of the underground mining in Paleolithic times, perhaps as early as 40,000 BC, miners confronted oxygen deficiency, toxic gases, harmful dust, and debilitating heat. As miners became more skilled by the first millennium BC, they learned to course the air through multiple openings or circuits to provide fresh air to the working phase, and to use fire-induced air currents. Control and processes. Individual conditioning processes are employed. In mining, they consist of the following. Number 1. Quality control. Purifying air and removing contaminants. A. Gas control. Vapors and gaseous matter, including radiation. B. Dust control. Particulate matter. Number 2. Quality control. Regulating magnitudes and directions of airflow. A. Ventilation. B. Auxiliary or phase ventilations. C. Local exhaust. Number 3. Temperature, humidity control. Controlling latent and sensible heat. A. Cooling. B. Heating. C. Humidifications. D. Dehumidification. Control processes can be used individually or collaboratively. If the goal is to complete mine air cooling, then all three objectives must be satisfied, and multiple processes can be used at the same time. Several procedures are possible, serve more than one purposes. For example, ventilations, the most prevalent in mining, service primarily for quantity control but may also serve for quality control and temperature humidity management. In coping with an atmospheric environmental hazard in mining, certain engineering principles are fundamentals and applicable to control of any contaminant. These contaminants consist of mainly of gases and dust but include heat and humidity as well. In order of preference of their applications, engineering control principles consist of the following. Number 1. Prevention or avoidance. Number 2. Removal or eliminations. Number 3. Suppressions or absorptions. Number 4. Containment or exhalations. Number 5. Dilutions or reduction. coordinations of mining and ventilation system. Despite its importance in the life support process, environmental control in mines present a conundrum. It happens in every business. On the one hand, environmental management is critical to the protection of human life and the operations of subterranean facilities. It is, on the other hand, a byproduct of the fundamental goal of mining. The extractions of the ore, rock, or coal from a mineral deposit. The paradox is the environmental regulations has no direct impact on productivity while allowing the manufacturing cycle to take place. The four highly important developments in the last 3 decades, 2 technological and 2 non-technical, are responsible. Foundations of mine ventilation. The field of ventilation and air conditioning is built on numerous disciplines. They manage the physical, chemical, and thermal characteristics of air using fundamental ideas from physical chemistry, thermodynamics, fluid mechanics, and mechanical design. Mining engineers use their understanding of mining operations to construct subterranean conditioning system when dealing with the more specialized topic of mine ventilation and air conditioning. They are, however, more constrained in their practice than mechanical engineers when it comes to dealing with industrial air cooling. As previously said, their principal airflows conduits must match with the apertures driven in the rock for mining reasons. Understanding mine ventilations and air conditioning thus necessitates understanding of both mining technologies and basic science. Fundamental concepts of fluid mechanics for mine ventilation. Fluid statics. Number 1. Pressure scales. 2 fundamental pressure scales are absolute pressure and gong pressure. Number 2. Law of perfect gases. An ideal gas is one in which the following theoretical conditions are met. The volume occupied by gas molecules is negligible compared to the total volume of gas. There are no forces of attractions or repulsions between the gas molecules and their container. There is no loss of internal energy due to collisions between gas molecules. Boyle's law. For a given quantity of an ideal gas that remains at fixed temperature, the pressure and the volume are inversely proportional. Charles law. For a given quantity of ideal gas that remains at fixed pressure, the volume are directly proportional. Gay-Lussac law. For the fixed volume of an ideal gas, the pressure and temperature are directly proportional. General gas equations. Ideal gas law. The general gas equation is stated as follows. For a gas in which pressure and temperature are kept constant, the volume it occupies is directly proportional to the number of the molecules. Number 3. Real gases. Van der Waals equations. To better model the behavior of real gases, Van der Waals established a modifications of previous equations, especially it corrects the pressure and volume terms. Number 4. Hydrostatic pressure. This type of pressure is due to a column of fluids on the object. The equation by which it's governed can be easily obtained from the weight and density of a mass of air contained in a column of height over its base area. This relationship is expressed mathematically as equation below. Then finally, P equals PGH. Fluid dynamics. Number 1. Types of pressure present in a moving fluid. A moving fluid has the following types of pressure. Static pressure. Static pressure is a concept comparable to atmospheric pressure or the pressure of gas-filled vessels. This type of pressure is the one that a fluid has regardless. Types of fluid pressure in the force conductions, static pressures, dynamic pressures, and total pressures of its speed. In addition, it is the same in all directions and can be positives or negatives. That is, it helps the flow or put up resistance. Dynamic pressure. This pressure is a measure of kinetic energy per unit volume possessed by a fluid particles in its path along a pipe. In other words, it is the type of pressure caused by the inertia of fluid particles striking a surface perpendicular to their movement. Mathematically, it can be expressed as the formulation below. Number 2. Pressure units. The Pascal or PA is the International System Pressure Unit. It is the pressure exerted by a force of 1 Newton on 1 meter squared surface normal to it. Other units exist. Their conversion factor are listed in the table below. From the definition of pressure as force per unit area. This relationship means that a pressure can be expressed in units of energy or work. In this way, it is possible to indicate that the ambient pressure is 1 atmosphere. Number 3. Energy conservations, Bernoulli's equations. It is assumed that a controlled volume of an incompressible fluid travels through force conductions. The sum of kinetic, potential, and due to pressure energies must be the same for any point of fluid under the principles of energy conservation, which is expressed as the formula shown below. If a fluid control volume is assumed in a pipeline, the particles to the left of control volume boundary 1 exert positive work. They act in the directions of favoring circulations. However, those on the right of control volume boundary 2 perform negative work, opposing the movement. The work exerted by these particles can be defined as the formula shown below. If then we apply the expressions of kinetic energy, 1/2 mv squared, potential energy and pressure energy, we have 1/2 m1 v1 squared plus m1 gh1 plus p1b1 equals 1/2 mv2 mv2 squared plus m2 gh2 plus p2b2. For each mass, m equals pb, where p is the density and b the volume. Therefore, 1/2 pb1 pb1 squared plus pb1 gh1 plus p1b1 equals 1/2 pb2 b2 squared plus pb2 gh2 plus p2b2. As the fluid is incompressible, the control volume crossing 1 and 2 is the same size and therefore has the same mass. Taking out the common factor, 1 arrives at 1/2 pb open parenthesis v2 squared minus b1 squared plus pbg open parenthesis h2 minus h1 equals open parenthesis p2 minus p1b, which amplifies 1/2 p open parenthesis b2 squared minus b1 squared plus pg open parenthesis h2 minus h1 equals open parenthesis p2 minus p1. Then regrouping teams leads to Bernoulli's equations shown below. This expression is stated as the sum of kinetic per unit volume, 1/2 pb I squared, potential per unit volume, and static energy per unit volume remains constant for any 2 points along a streamline. Sometimes, the Bernoulli equation is regrouping as follows: P1 over Pg plus B1 squared over 2G plus Z1 equals H1. Number 4. Continuity equations and Bernoulli's effect. The continuity equation is nothing more than the law of conservation of mass applied to the flow of fluid through a conduct. Therefore, you have that equation below. PA1B1 equals PA2B2, where P is the density of the fluid, A is the cross-sectional area of the duct, and V is the velocity in the sections considered. The above expressions finds its most characteristic example in the Venturi effect. This is the reduction in static pressure when the fluid velocity increase in the constricted sections of a duct. Thus, for the continuity equation to be fulfilled, if area A2 is smaller than the area A1, velocity V2 will be greater than V1 and PV2 will be higher than PB1. According to Bernoulli's expressions, an increase in the dynamic pressure in one of the sections implies a decrease in static pressure, which translates into static pressure P2 being less than P1. Similar reasoning can be made for area cross sections A3 of figure 1.7 with respect to area cross sections A1 and A2. Number 5. Measurements. It is important to note that the measuring elements located perpendicular to the surface of the ducts through which a fluid circulates provide static pressure. On the other hand, measurements made in the directions of flow indicates total pressure. If part of the total pressure is compensated by the static pressure, then the resulting measure is of dynamic pressure. Number 6. Conservation of linear momentum. To immobilize a tennis ball traveling at 200 km/h raised to the power of -1 in a time simpler than to stop at the same time a vehicle that moves at the same speed to evaluate the effects of motion. Therefore, necessary to know not only the velocity of the bodies but also their mass. This can be done using the kinetic energy equation. However, what cannot be considered is the time it takes for the body to stop. It is, therefore, necessary to have an expression to explain this phenomenon. Thus, for the interacting bodies, F1 is the force exerted by M1 in the MB and F2 by MB in the MA we have by Newton's second law that equation show below. Number 7. Viscosity. Viscosity is a characteristic of fluids that represent their resistance to flow. Conceptually, it responds to the internal friction. Conceptually, it corresponds to the internal friction's force between sheets in contact with a moving fluid. Formally, it is the relationship between the shear force and the speed gradient. It can be expressed into two forms: dynamic viscosity in direct applications of the definitions and whose unit are kilogram m-1 s-1 or b. Velocity profile on the fluid circulation through a duct. A. Laminar. B. Turbulent. Kinematic viscosity, which is the dynamic viscosity divided by the density of the fluid, in which case the units are m² s raised to the power of -1. According to the above, kinematic viscosity can be written as B equals mu over P. Number 8. Laminar and turbulent flow. Reynolds number. There are three fundamental fluid flow regimes: laminar, turbulent, and transition. The velocity distributions in the cross-sections of a duct is different in each of them. Thus, the profile will be parabolic if the flow is laminar, and in the turbulent regime, the parabola will tend to flatten out as the turbulence gets higher. In a like manner, when a fluid flows on a plate, minimum velocity is reached in contact with the plate. Then, the speed increases with distance from the plate up to a point at which it remains constant. The Reynolds number is a dimensionless number whose square root is inversely proportional to the distance from a surface at which the liquid velocity remains constant. This number arises from the relationship between inertial and viscous forces acting the fluid. Speed profile of fluid moving on surface and boundary layer. A. Cross-sectional area meter squared of the duct. O. Perimeter. Making use of equation 1.17, the Reynolds number can be defined as RE equals PdH over B for air kinematic viscosity between 1.42 times 10 raised to the power of -5 m² s raised to the power of -1 open parenthesis 10 Celsius and 1.60 times 10 raised to the power of 5 m² x raised to the power of 1 open parenthesis 30 Celsius. It can be written that RE equals 67,280 dHb. The Reynolds number delimits the change between flow regimes. The limits vary depending on closed conduits, flows, or open flows. Thus, for a circulation pipe, if RA is greater than 103, the regime will be turbulent, whereas for fluid flowing over flat clay, this same regime is reached at RE greater than 3.5 times 105 minus 1 times 106. In the mining galleries, it is frequent to indicate that if RA is less than 2000, the flow is in the laminar regimes, and if RA greater than 4000, the flow is turbulent. Between 2000 and 4000 is the transitions regime. Novetzke 1962 that the change of regimes from laminar to turbulent in the mining stopes occurs at RE around 1000 to 1500. Number 9. Friction losses. As air flows through a duct or gallery, it loses energy due to friction between fluid layers as well as friction between air and walls. In particular case of mining, they account for 70 to 90% of total mine losses. Figure 1.11 depicts the static pressure losses suffered by water pipe due to friction when circulating through a horizontal pipe. Total pressure losses by friction of a fluid with the walls of duct can be calculated using the Darcy-Weisbach equation. The coefficient of friction is usually calculated using the Moody diagram or multiple expression. If the regimes as laminar and the duct has a circular cross-section, the Hagen and Feisserel equation can be used, shown in equation 1.23. If the regime is turbulent, various expressions are better adapted to reality according to the type of duct. If the flow of turbulent RA less than to 10 raised to the power of 5 and the duct is smooth, the coefficient of friction depends more on the Reynolds number than on the roughness. In this case, the Blasius equations 1913 can be used, equation shown below. If the flow is turbulent and the duct very rough, the roughness has much more influence than the Reynolds number, which has almost no influence. In this case, the Nekurad formula applies, shown below. Number 10. Shock losses. Any variations from a straight duct of constant cross section generation shock losses. These losses, from a physical point of view, are due to variations in the momentum as a consequence of charges in direction, speed and acceleration in fluid molecules. They are usually divided into A. Those due to charges of direction such as air blows, joint or splits. B. Those resulting from variations in the cross-section such as obstructions, expansions, construction, entrances, and exits of fluids in the duct. A theoretical demonstrable example of this type of losses is what happens when fluid circulates inside a pipe and suddenly an orifice is found, in which case one of the most notable effects is its contractions in the form of vena contracta. Therefore, starting from the Bernoulli equations, assuming that there are no viscous losses and that the flow is laminar, we have that P1 over P plus B1 squared over 2 equals P2 over P plus B2 squared over 2.